Welcome everyone, and thank you for coming for Meita Asami-san's talk. So he is giving a presentation today that probably came from his PhD thesis. Yes. So Meita Asami did his bachelor and his master in electrical engineering at the Tokyo University, and in 2020 he received the student award at the PVSec conference. He published 3 first author peer-reviewed journals, and he's focusing now his research on the development of high-efficiency 3.5 solar cells under Professor Sugiyama-san. So that is all at Tokyo University, and it looks like he will stay there for a long time. He just submitted his PhD thesis, and so he's waiting now for the confirmation of his title. So thank you very much for coming, and the floor is yours.
Yep. Thank you for your kind introduction, Hina-san, and thank you for inviting me to make this presentation, and thank you for coming. And today I will talk about what causes voltage loss in solar cells. They are my colleagues, and they are my supervisors. And I'm belonging to Sugiyama laboratory, and I'm working on the optimization of quantum structure for high efficiency multi-junction solar cells. And this is the abstract of my talk. We propose a new voltage loss analysis technique for quantum structure solar cells. There are 3 types of voltage loss. I will explain them later. And we found that voltage loss in conventional quantum structure solar cells were larger than that of the bulk gallium arsenide solar cell. And based on this voltage loss analysis, we designed new quantum structure, and it achieved the lowest voltage loss, as you can see. And we believe that this voltage loss analysis is also useful for the development of other types of solar cells, such as perovskite and CIGS solar cells. And this is the abstract of my talk. I've already talked about the... so this is the outline of my talk, and I've already talked about the abstract, so I would like to start from the background. And this is a conventional germanium-based triple junction solar cell. And as you may know, multi-junction solar cells can utilize wide range of sunlight spectrum. However, the current is restricted by the middle cell due to the excessively high band gap, 1.4 eV. So to enhance current density and energy conversion efficiency, we must adjust the band gap of middle cell to 1.2 to 1.35 eV. And by lowering the band gap of middle cell, we can increase the amount of So we can increase the amount of carrier generation in middle cell like this. And superlattice is one of the candidates. We can use indium gallium arsenide, and that has narrower band gap and a larger lattice constant than gallium arsenide by growing indium gallium arsenide and gallium arsenide phosphide thinly and alternately, and the energy levels in the quantum wells can be adjusted like this by changing the composition and the width of wells and barriers. But the carrier collection efficiency of the superlattice solar cells is low due to the carrier confinement effect in quantum wells. Although the band gap is suitable, the current density becomes low. To solve this problem, I was working on the research of wire-on-well. These are the cross-sectional TEM image of each quantum structure. And this is the direction of crystal growth. And planar superlattice is a common superlattice. And wire well is grown on 6-degree misoriented gallium arsenide substrate, while the planar superlattice is grown on gallium arsenide 001 substrate without misorientation. As you can see, wire structure wire structure has distinctive undulated patterns, and this is the surface of wire structure. When we grow superlattice on misoriented substrate under suitable temperature, step bunching occurs and wire is formed spontaneously. And we expected that wire can achieve better carrier correction since there are thin barrier area here, and carrier tunneling effect can be enhanced at thin barrier. As we expected, the wire achieved a higher current density. And this is the solar cell structure we fabricated. And these are JB and EQE results. So from these results, we can say that wire is suitable to achieve a high current density. Thinner barrier area may have boosted the tunneling probability of photogenerated carriers. In my preceding study, I measured the effective carrier mobility here. And the carrier mobility in wire is higher than that in normal planar superlattice. So that's why wire solar cells achieved high current density. But open circuit voltage of wire solar cells is lower compared to other types of solar cells. So why is the open circuit voltage of wire solar cells low? And to answer this question, we need an accurate voltage loss analysis technique. Here we have 4 solar cells which have different VOC. If this cell is a bottom cell, we can say that this VOC is quite high. But if this is a middle cell, we can say that this VOC is quite low. So without the information of band gap, we cannot evaluate the quality of voltage. In addition, the word quality of voltage is very ambiguous. So for the development of solar cells, voltage loss must be evaluated accurately, and the cause of the loss must be clarified. Then how can we evaluate voltage loss? I think the band gap offset, WOC, is the most famous field merit for open circuit voltage. However, as Professor Ned pointed out in 2018, WOC must not be applied to quantum structure solar cells. So we need other technique. And we found that voltage loss analysis based on detailed balance theory can be applied to quantum structure solar cells. Here I will explain about voltage loss analysis based on detailed balance theory. This equation was proposed by Professor Lau in 2017. And I don't want to do mathematics and physics classes. Maybe you are going to sleep. So the important thing here is the voltage loss equals to the difference of open circuit voltage at Shockley quasar limit and measured open circuit voltage. As you know, for the calculation of VOC at Shockley quasar's limit, we need band gap for the calculation. So we have to define the effective band gap of quantum structure solar cells. And we propose the definition of band gap of quantum structure solar cells. There are many ways to define the band gap of solar cells, but all of these methods are not suitable for quantum structure solar cells. So we propose a new method. To define the effective band gap of solar cells, let's think what's the main objective of lowering the band gap of the middle cell. It is the enhancement of current density. To enhance current density, we must expand absorption edge like this. But as you know, expansion of the absorption edge to lower energy results in the decrease of open circuit voltage. So ideal material and structure can be defined as increasing photogenerated carriers with minimized expansion of absorption edge. To define the band gap, first we calculate the first derivative of EQE, this blue line, and regard the peak at the highest energy as a standard band gap. Yeah, so we regard the peak at the highest energy as standard band gap. And then calculate the generated current by expanding absorption edge, and we can calculate generated current density by this equation. Integration from 0 to standard band gap. Then next obtain maximum value of EQE. And then calculate effective band gap from this equation. If the EQE of real solar cell were like this, we don't have to expand the absorption edge to lower energy like this to enhance current density. So this is the effective band gap and ideal band gap of quantum structure solar cells. And we can calculate it using this equation and numerical calculation. So now we can calculate the effective band gap of quantum structure solar cells here and VOC at Shockley quasar's limit. I will not explain it in detail, but we slightly modified the conventional method like this. And this modification is needed for low EQE samples. But anyway, this part is too detailed and not important for today's talk, so I will skip it. So short circuit current voltage loss and radiative recombination voltage loss and non-radiative recombination loss are defined by these equations. But these are not easy to understand intuitively. So here I will explain it using analogy of water and bucket with 3 types of holes. An ideal solar cell has step-like EQE, so more water is coming into the bucket compared with real quantum structure solar cell. The difference of water coming in corresponds to this EQE, this green EQE area with the convolution of sunlight flux. And short circuit current density of ideal cell is higher than real quantum structure solar cell. And the real quantum structure solar cell has short circuit current voltage loss about 3 millivolt. And 3 millivolt is quite small, and usually short circuit current voltage loss is negligible. So this short circuit current voltage loss, this is the short circuit current voltage loss. And next I will explain non-radiative recombination voltage loss. Non-radiative recombination voltage loss might be the most familiar voltage loss to all of you. If there are crystal defects, carriers recombine non-radiatively and their energy is lost as heat. And we can evaluate non-radiative recombination voltage loss with either EQE or EL measurement. I have already talked about this at UNSW last August, so if you want to know it in detail, please read my published journal article. Non-radiative recombination voltage loss is caused by the loss of energy as heat. So then at last I will explain radiative recombination voltage loss. Radiative recombination voltage loss is caused by the excess expansion of absorption edge. And radiative recombination voltage loss is defined by this equation. Photon flux of blackbody radiation plays an important role. Photon flux of blackbody radiation at lower energy is much higher than higher energy. So this part of EQE significantly increase the diode saturation current of real solar cell. And these are calculated diode saturation current. And these values are used here. This part of EQE resulted in 8.6 times a larger value of diode saturation current, and it resulted in 67 millivolt voltage loss. In this water and bucket analogy, it corresponds to a larger hole of bucket, and more carriers recombine radiatively, and it lowers the level of water, so open circuit voltage. Then I will show you an example of voltage loss analysis. This analysis has been done to the same samples which I showed you. And these are the results. As I explained, short circuit current voltage loss is very small. And quantum structure solar cells have higher, larger voltage loss compared to the bulk gallium arsenide reference sample. Quantum structure solar cells have lower non-radiative recombination voltage loss, but the radiative recombination voltage loss is much higher compared with bulk gallium arsenide solar cell. This is a graph of radiative recombination voltage loss. Radiative recombination voltage loss is dependent on the types of quantum structure. So we need to design a new quantum structure to reduce radiative voltage loss. Then how to reduce the voltage loss in quantum structure solar cells? As I explained, excess expansion of absorption edge results in radiative recombination voltage loss due to the profile of blackbody radiation flux. So steep absorption edge is indispensable for the suppression of radiative recombination voltage loss. So this slope results in this radiative recombination voltage loss. Then how can we achieve steep absorption edge? Here we focus on the thickness of quantum well. When you grow a 3-5 semiconductor quantum structure, there will be interface diffusion and the thickness fluctuation. Let's say if the thickness of quantum structure is 4 nanometer and there is plus minus 2 nanometer thickness fluctuation, the energy level will fluctuate about 51 milli eV. But if the thickness is 12 nanometer and there is plus minus 2 nanometer thickness fluctuation, it will be only 18 milli electron volt energy level fluctuation. So thicker quantum well is better to reduce radiative recombination voltage loss. And we proposed this new quantum structure. I'm now writing a thesis about this structure, so I will skip the details today. And this is the structure of entire cell and EQE results and JV results. We call this new quantum structure as ultra thin barrier planar superlattice, UTB PSL. And this structure realized steeper absorption edge compared to a conventional quantum structure. And it realized high open circuit voltage. Our new quantum structure solar cell achieved low voltage loss. Steep absorption edge successfully suppressed radiative recombination voltage loss. And the reason is not clarified yet, but low enzyme composition, thick quantum layer might enhance crystal quality, and reduce the non-radiative recombination voltage loss. And from EQE and JV results, we can roughly estimate that the energy conversion efficiency of conventional germanium-based triple junction solar cell module, so we can increase the efficiency of conventional germanium triple junction solar cell from 29.5% to 30.9% by using this new quantum structure. And this is the conclusion of my talk. We proposed accurate and easily available voltage metrics for the evaluation of quantum structure solar cells. We revealed the importance of radiative recombination voltage loss in quantum structure solar cells. And our voltage loss analysis can be applied to other type of solar cells, such as CIGS and perovskite solar cells. If you want to test, I can send you my Excel file and it automatically do this voltage loss analysis. And based on the voltage loss analysis, we proposed a new quantum structure. Steep absorption edge successfully reduced radiative recombination voltage loss. We believe that voltage loss analysis is indispensable for the development of new solar cells. Yep, that's all. Thank you for listening.
Thank you very much for this wonderful talk. It is up for discussion now. Please, if you have any question, raise your hand.
Thanks for the nice talk. I have one question about the definition of the effective band gap. Because I realized the extended absorption is normalized to the highest EQE.
Yes.
Why not normalize to the average EQE? The average EQE.
Average EQE. Because if we use the average EQE, the shorter wavelength region will also affect the average EQE. And for the definition of the effective band gap, we want to omit the effect of shorter wavelength region, because the shorter wavelength region does not affect the band gap. Only the longer wavelength region affects the band gap. So I think if we use the average EQE, yeah.
The effective band gap will be lower.
Yes, and it will give us unphysical value of voltage loss.
Okay, because the shape of the EQE is that affected by the optical, some kind of optical loss.
Yeah, and the surface reflectance and the quality of window layer. Yeah.
Thanks for the nice talk. I have a question about the radiative recombination loss. You introduced this new quantum structure. You said you suppress the radiative recombination loss. So you said it might comes from the improvement of the crystal quality.
No, that crystal quality affects non-radiative recombination.
Okay, can you go back to the slides? So in your conclusion, I see. So can you comment why this new quantum structure improve the radiative recombination velocity?
Yep, because new quantum structure has steeper absorption edge. And if the absorption edge is gradual, we will have a higher value of diode saturation current. But this, how to say, a very low EQE tail doesn't help us to increase the short circuit current density, right? So we have to realize the very steep absorption edge to reduce radiative recombination voltage loss and to achieve high energy conversion efficiency. Yeah.
Wonderful. Thank you so much. Oh, one more question. Please go ahead.
Yeah.
Thank you.
If you compare the VOC loss of different kind of structure, you can see you propose the model has lowest VOC loss, right?
Yeah.
Can you move to this slide? Yeah, I can understand the radiative loss of your proposed model is still larger than the bulk gallium arsenide because you introduce some quantum structure and the fluctuation of band gaps cannot be avoided, right? I mean, because you have the quantum structure, then so it will have some kind of band gap fluctuation, like fluctuation. I mean, the band gap changes because you have the fluctuation of the thickness of each structure. So it will of course lead to some kind of band gap structure, band gap fluctuation. So is this why the radial to VOC loss is still larger than the bulk gallium arsenide?
Yeah, so even if we tried to make the absorption edge steep, because between the gallium arsenide phosphide and indium gallium arsenide, we have some kind of interlayer, like indium gallium arsenide phosphide, and that layer will make the absorption edge more gradual compared with bulk material solar cells. So yeah, we couldn't achieve as low to gallium arsenide.
So another question is about the So about the non-radiative to recombination, it's reduced compared to the bulk gallium arsenide. Is that because of the quantum confined effect?
Yeah, I think so, but the reason is not clarified yet. But if we confine the carriers in very small space, I think the carriers will recombine more radiatively. So the crystal defects are filled with carriers, and non-radiative recombination will be saturated. So yeah.
So what I don't understand is how this changed compared to the other quantum structure.
Yeah. So maybe this time for new quantum structure, I used very low composition of indium, and for the conventional quantum structure, I used 30%, so 0.3 indium content indium gallium arsenide, and usually indium gallium arsenide, which has higher indium composition, have lower crystal quality in our crystal growth machine. So maybe that's the reason why we achieved higher crystal quality and lower non-radiative recombination loss this time.
Thank you very much.
So, okay, wonderful. I guess that concludes today's talk. Thank you very much for coming, and let's thank Meita Asami again.
Thank you.